everyone, welcome to IIT-JAM in Chemistry tutorial number 10, and in this tutorial number 10 we are going to have lecture number 6 on the chapter Atomic and Molecular Structure, where the topic of discussion is postulates of quantum mechanics. And in this context we are also going to discuss normalized and orthogonal wave functions, its complex conjugate. Along with that, the idea about complex numbers will also be discussed, and finally, the significance of psi star will also be discussed in this lecture. So let's start from the postulates of quantum mechanics, postulate number 1, where we are going to have some idea about stationary and non-stationary states. First of all, what about the postulate? The postulate states that the physical state of a particle is described as fully as possible by an appropriate wave function psi, which is a function in turn of x, y, z and t, where x, y and z are the three Cartesian coordinates and t is time. So this is the first postulate, and from this postulate we can have some idea about stationary and non-stationary states. If here time is included, then it would be non-stationary, whereas if time is excluded, it would be stationary function. So the state that is determined by time included wave function psi, which is in turn a function of x, y, z and t, this is non-stationary, while the state that is determined by time excluded function, that is psi must be a function of x, y and z only, then this is stationary. Move on to the postulate number 2. The postulate states that the probability of finding a particle in the space within R and dr is given by psi star r psi r dr, where dr is x dx dy dz. Psi r is the function and psi star r is its complex conjugate. So we are going to have some idea about complex conjugate from this postulate number 2, and let's discuss. If I is such a number which is not a real number, which is a complex number or imaginary number, which is actually root over minus 1, and with the value of I we're describing some function psi r as a plus ib, then its complex conjugate will be described as a minus ib. So this is psi star, okay, and their product must be something real. That means a plus ib into a minus ib must be a square plus b square. We know that. Hence this is some real function, okay, and its integration over the range r1 to r2 with dr is actually the probability of finding the particle in a finite interval. Here why it is finite? Because r is some finite number, r1 r2 both are finite numbers, and there is only one particle, and suppose there is only one particle, suppose one electron on the hydrogen atom, okay, then in that case the value the range should be minus infinity to plus infinity, and the value should be 1. So integration r1 to r2 of psi star r psi r dr is probability of finding the particle in a finite interval between r1 and r2, and if there is only one particle anywhere in space, this point is important, anywhere in space, that is why minus infinity to plus infinity, then the probability of finding the particle is integration minus infinity to plus infinity of what? Psi star r psi r dr, and that must be equal to 1. Now move on to postulate number 3, where we are going to have some idea about eigenfunction and eigenvalue. The postulate states that the only possible value that can be observed of a physical property like angular momentum, energy, etc. of a system are the eigenvalues lambda in the operation equation. This one, a cap psi star equals to lambda psi r. A cap psi r equals to lambda psi r, where a is the operator, a is some operator for the physical quantity, and what we are looking for, the physical quantity, what we are looking for, and psi r is the well-behaved eigenfunctions. So what about a well-behaved eigenfunction? Let's elaborate this postulate here. So what about well-behaved eigenfunction? Okay, here is the three-dimensional form of the Schrödinger wave equation, which is time independent, and this is the equation Laplacian psi 8 pi square m by h square into e minus v psi equals to 0. This is the 3D form of the time independent Schrödinger wave equation, and This equation in turn is actually a second order differential equation that may give rise to several solutions through, though not necessarily all of them correspond to any physical or chemical reality. That means it may have a number of solutions, but all of them cannot be accepted. Such wave functions are therefore considered unacceptable. Since they are not accepted, so they are unacceptable. So for acceptable wave function, psi must be a well-behaved wave function. Now what are the conditions for psi r to become a well-behaved wave function? And the conditions are: number 1, this psi r is single valued. Number 2, psi r and d psi r dr is continuous. That means there should be no discontinuity in the value. And finally, number 3, psi r must vanish at infinity for bound state. That means it will not be found anywhere in the state beyond the boundary. Okay, so psi r must vanish at infinity for bound state. And if it is a complex function, then the product of the function with the complex conjugate, that means psi star r psi r must vanish at infinity in that case particularly. So these are the conditions. If psi r follows properly, then it would be a well-behaved wave function, and the corresponding value of lambda must be a well-behaved, must be some Eigen value. That means some physical or chemical property. That means this value can be accepted. And next we have postulate number 4, where we are going to have idea about operator. In the previous postulate number 3, we denoted something about operator. A cap was some operator. Now first of all, let me read out this postulate, then we are going to discuss the idea about operator. So what about the postulate? To every dynamical variable such as position, velocity, linear momentum, angular momentum, energy, etc. of a system, there corresponds a linear operator in quantum mechanics. This is the most important postulate of quantum mechanics. Now what is an operator? An operator is symbol for a certain mathematical procedure which transforms one function into another. And what about a linear operator? If f and g are any functions, any two functions, then a cap will be a linear operator, provided after the operation it can be separated into two separate functions with the operators. That means a cap f plus g is equal to a cap f plus a cap g. For example, root over, the operation, mathematical operation of root over, is not at all a linear function, because not at all a linear operator, because root over g plus h is not equal to root over g plus root over h. But del x is a linear operator. Here is a typing error. This is not a function, this should be operator. Okay, so root over is not a linear operator. If you are taking some note from this, then write operator here in place of function. It is misspelled here. Okay, not misspelled, actually mistakenly written function instead of operator. We have another example of a mathematical function, mathematical operation, which is del x, and this operation can be done in a linear way, because if you differentiate g plus h, then separate differentiation of g plus h can be added up. So del x of g plus h must be equal to del x of g plus del x of h. Therefore, from that context, del x is a linear operator, while root over is not a linear operator. Now postulate number 5, where we are going to have idea about normalized and orthogonal wave function. This postulate states that when a great many measurements of any dynamical variable are made on an assembly of system whose state function is psi, the average value obtained is given by average A as this expression, integration minus infinity to plus infinity of psi star a cap psi d tau divided by integration minus infinity to plus infinity of psi star psi d tau, where psi is not normalized and d tau represents an element in the configuration space. So this is the postulate. This is quite difficult to understand. without the following discussion. Here is the discussion on the basis of which it may be a little bit clear about this postulate. The probability function, that means psi star psi modulus or simply psi square modulus. This may be psi square modulus if it doesn't have any complex conjugate. That means it is not any complex number, the wave function. In that case, psi and psi star both are equal. In that case, psi star would be psi square. So for such a probability function, when undergoes integration over all space, that means this is the actually volume function. That is why this is the integration over all space, minus infinity to plus infinity psi square d tau. And if this is equal to 1, then this is normalized. Okay, and if it has some complex character and along with its complex conjugate, if it is integrated over this space with the volume function, then if its value is 0, then it is said orthogonal. So this is the idea about normalized and orthogonal. Okay, so psi is not complex. In that case, psi equals to psi star, and psi star d tau becomes psi square d tau, and integration over all space becomes 1. If it becomes 1, then the function is normalized wave function. And if it has some complex character, then along with its complex conjugate value over the space, if it is integrated and if it produces the value 0, then the wave function is said orthogonal. So this is about the postulate number 5. Now move on to postulate number 6. This is yet another important postulate in the quantum mechanics, and we are going to have the energy operator function, which is known as Hamiltonian. So the postulate states that the time development of a wave function is given by, here t is now being introduced, I h cross d psi dt equals to Hamiltonian psi. This operator is known as Hamiltonian. Capital H cap is Hamiltonian, which is the time dependent Schrödinger wave equation. This equation is actually the time dependent Schrödinger wave equation, where H cap, capital H cap, is the Hamiltonian operator, and H cross, in short, it is written instead of H by twice pi. So in several times in this topic, H by twice pi may be written as H cross. Now, if a beam of electrons traveling along x direction can be treated as a wave, okay, then the propagation along the x-axis, it is propagating along the x-axis. In that case, we know the sinusoidal form of the wave equation number 11 is psi equals to a sine twice pi by lambda into x. We have already discussed this equation during derivation of the Schrödinger wave equation, which was time independent. Okay, so this is the actually the changing amplitude of a sinusoidal wave function, and this is equation number 11. Okay, so if a beam of electron is traveling along the x direction, then it is propagating along the x-axis. Okay, it is propagating along the x-axis, and in that case we have the sinusoidal form of the wave function. Y, actually y is substituted as psi, and psi is nothing but capital A sine twice pi by lambda into x, where A is the maximum amplitude, lambda is the wavelength, and x is the displacement along x-axis. Okay, so this is equation number 11. Now let's move forward. An equivalent form of the time independent wave function is, now we had the equation this one. Now this equation has another form, equivalent form, which is this one. Psi is c exponential plus minus twice by I by lambda. This is equation number 16 here. Now if this equation is differentiated both sides with respect to x, then the result is plus minus twice by I by lambda into c, again exponential plus minus twice by I by lambda. And this value c into exponential plus minus twice by I by lambda is actually psi. So instead of that, we are writing here psi, and this way we are getting equation number 17. Now if px is the linear momentum along x-axis, then according to the Broglie equation we know the expression of linear actually the momentum with lambda relationship, and this relationship is lambda equals to h by p, and here along the x-axis it is h by px. So let's put this value here in this equation number 17. Then what we get here? Now here in place of lambda we are putting h by px. Okay, and this way we are getting it is plus minus px into twice by I by h into psi. So this pi, if taking to the denominator here, then it goes to the denominator of h and it becomes h cross. So that is why instead of twice pi by h we are writing h cross here in the denominator. So this is px plus minus px into I by h cross, then psi, and finally we can rearrange this as plus minus h cross by I d psi dx, actually del psi del x equals to px into psi. So we are, if this operation is done, then px is obtained. That means this is actually the linear momentum operator along x-axis. Okay, look, this is the operator, this is the wave function, and this is the lambda value, that means the Eigen value, and again the wave function psi is obtained. So this way the operators are determined. Here we are going to have the linear momentum operator, this one along the x-axis. So thus the linear momentum operator along x-axis may be set up as p. These two equations, equation number 18 and 19, since this is having some complex number, then the plus sign will go to px cap and the minus sign will go to px cap star. Okay, so since it is plus minus h by I cross del del x, then it may be divided into two parts, as one simple, another as its complex conjugate. Actually this is not simple, this is complex, and this is conjugate, this is its conjugate. Okay, this is not at all simple. And similarly, if x is replaced by y here, here, here and here, then correspondingly equation number 20 and 21 will be obtained. This would be the linear momentum operator along the y-axis. Similarly, the linear momentum operators along the z-axis would be obtained by replacing x with z here, here, here and here. Okay, so this way equation 22 and 23 are obtained, which are representing the linear momentum operator along z-axis. Okay, the classical expression for the total energy, that means kinetic energy plus potential energy of a single particle of mass m, is called Hamiltonian. So this is the definition of Hamiltonian, and it is denoted as capital H, and its expression has h, capital H, equals to half mu square. Mu is the linear velocity and v is the potential energy. Okay, and it is also as a function of x, y, z and t, that is time t is involved already here, and x, y, z if taken together as r, that means the polar value, that means r square is x square plus y square plus z square, we know that, then polar coordinate, then it may also be replaced by r, then r comma t, as v is a function of r and t. Okay, potential energy, and here half mu square can also be written as mu whole squared divided by twice m, and actually mu is the linear momentum along any axis, that is why no suffix is given here. So this is p squared divided by twice m in plus potential energy as a function of polar coordinate r and time t, and thus this way we get equation number 24. In terms of its three components, that means along the x, y and z axis it definitely has three components, then p square can be written as p square equal to px squared plus py squared plus pz squared, and if this value as three components, the value of p square as a function of its three components is replacing this p square in equation number 24, then we shall have this, have the expression of h as a summation of two terms. In the first term, in the numerator we have px squared plus py squared plus pz squared, and in the denominator we are having twice m. plus the second term is the potential energy as a function of the radial function and time. Now with equations 18 to 18 and 22, the operators say px cap squared is taken to mean, that means you have, let's have a look, this is equation number 18. Okay, so here if px square is taken, then it is meaning that this operation is repeated twice, so that px cap squared plus py cap squared plus pz cap squared equals to the two operations sequentially. So this one the x operation, this one the x operation. This means this is px cap squared, this is py cap squared, and this is pz cap squared. Now take h cross by I as common, then we are having h cross by I twice, that means their whole square, and finally what is left is the Laplacian function. So my 1 by I whole squared is actually minus 1, that is why it is minus h cross squared, and here it is Laplacian, and it is shown here that h cross by I whole squared is nothing but equal to minus h cross squared. Now this, if this value of px cap squared plus py cap squared plus pz cap squared substitutes the value px square py square plus pz square in equation number 25, that means here in this equation, this is the expression of h. Now the expression of, in order to get the expression of h cap, we have to replace px as px cap. Okay, this is the expression of h, normal energy function. But if you want to get the operator for energy, corresponding operator for energy, you want to put a cap on h, then you have to put some cap on px also, and in order to do that, you have to substitute these three values as their corresponding operators, that means px cap squared, py cap squared plus pz cap squared. Okay, then h will take the form h cap, and thus the expression of the Hamiltonian operator, this is the Hamiltonian operator, and this will be obtained as this one. Okay, equation number 26. So the expression of the Hamiltonian operator is h cap squared by twice m Laplacian plus potential energy as a function of radial function and time. This equation number 26 is thus the expression of the Hamiltonian operator, and this expression can now substitute h cap in equation number 15. What is equation number 15? Look back the postulate on the basis of which we are deriving the expression of h cap. This is equation number 15, postulate number 6. IH cross del psi del t equals to h cap psi, and we have now got the expression of h cap, which will be substituted by the expression from equation number 26, what we have just obtained here. This is equation number 26. Okay, so the expression in the right hand side of equation number 26 replacing the first term, that means the left hand side of equation number 15 here. So h cross squared by twice m Laplacian plus potential energy as a function of radial function r and t. This is operating psi and producing IH cross del psi del t. This is equation number 27. But this is in the Cartesian coordinate. If it is transformed into the polar coordinate, then it takes the form del 2 del r square in place of Laplacian. So equation 27 represents the expanded form of the time-dependent Schrödinger wave equation. So this is very important, equation number 27. This is the time-dependent Schrödinger wave equation, and in terms of polar coordinate, Laplacian may be substituted by del 2 del r square. In that case, equation 27 takes the form this one. In the left-hand side, we are having h cross squared divided by twice m and del 2 psi del r square just in place of Laplacian. And here, the potential energy function, potential energy operator operating psi. Here in the right hand side we are getting IH cross by del t of psi. This is equation number 28. So that's all about all the postulates of quantum mechanics, postulates number 1 to postulate number 6. Now let's solve some questions. This is question number 21. It came in IIT-JAM 2021. If psi as a function of x, y and z describes the wave function of a particle, the probability of finding the particle between x and x plus dx, y and y plus dy, and z plus dx. We know that it is very simple. It is modulus, just simply modulus of what? Actually, if you do not even give the modulus, then also it will give some real value. Just product of the two functions. One is the main function, another is its complex conjugate. So what should be the value here? it is not, it is simply the product. Okay, and this is actually modulus is given, but dx dy dz's are outside. Here C, this is the correct option. Okay, here psi star x as a function of xyz and psi as a function of xyz, and then dx dy and dz. Okay, so this is the correct answer, and this one definitely not. This is, if it's like in case of single electron, this value is definitely 1. Okay, so this is the actually integration term. So the correct option is this one, the probability function. This is the probability function. Okay, then you have to integrate this. Then if it's a single electron, then it will produce the result 1. So the correct option is C. Question number 22. The wavelength for a particle moving in a ring is twice pi to the power minus half e to the power twice pi phi, twice I phi, where phi is the polar angle. The probability of finding the particle in a small interval d phi when the value of phi is pi by 2. So we have to find the probability of calculate the probability of finding the particle. So let's calculate this. Okay, so let's start from psi. The expression of psi, it is actually twice pi to the power minus half. That means this is e to the power something twice I phi divided by root over twice pi. So this is written as this one, and its complex conjugate must be the negative function. That means in the power of exponential there should be some negative value. Okay, and the probability is what? Probability is just, we have calculated in the previous question, just the psi star into the space function. Okay, so psi star into d phi. Okay, so just product, take the product, the value of psi, the value of psi star, then d phi, and then find out the calculation. Just calculate this one into this one, d phi, e to the power twice I phi minus e to the power twice I phi. That means what? E to the power 0. E to the power 0 means only 1. So it is 1 by 2 pi into d phi. That means d phi by twice pi. So here the correct option is option this one, option B, d phi by twice pi. Okay, so this came in 2006 JAM exam. And finally, this is the last question. This is actually appearing mistakenly. Let me rectify this. Okay, this is rectified. This was actually start. Okay, let me read out the question. Actually there is one more question, 24 is also there before conclusion of this lecture. So the normalization constant a for the wave function psi as a function of phi is a exponential I m phi, where phi has the range 0 to twice pi. So what is the normalization constant value of a? So how to calculate this normalization constant? So we have the expression of psi as a function of phi. This is a exponential I m phi. Therefore its complex conjugate must be exponential negative power of the same thing. So it's integration over the space. If this is equal to 1, as discussed in the postulates in the of quantum mechanics, if this value is 1, this is normalized. So we are just putting the value equals to 1 by integrating over the space 0 to twice pi, because here the range 0 to twice pi is given. Okay, and in order to get the value of psi star, you have to take the product of these two things. Okay, and the product is definitely this one into this one. That means a squared into e to the power I m phi minus I m phi. So e to the power I m phi minus I m phi, that means e to the power 0. That means only d phi is left here, and integration of d phi from 0 to twice pi is nothing but twice pi. And if overall value is 1, so a squared plus into twice pi equals to 1. That means a has the value 1 by root over twice pi. So this way the normalization constant is obtained, and the correct option is 1 by twice pi. This one, correct option is A. And last but not least, here is the final question of this lecture. X cap is an operation which is multiplied with x, and px cap is yet another operation which is h by twice pi I into d dx. Then what is the value, or what are the values of p cap x, px cap, x cap minus x cap, px cap? That means we have to check whether this one commute, these two operators commute. They are commutators. Okay, so if this value is not 0, then they do not commute. Okay, so let's check. H by twice pi is h cross by I, as we know. So let's operate first by multiplying with x, then followed by operating by px cap. So here psi x is multiplied with x, then this result is operated by px cap. Px cap is this one. Okay, so h cross by I ddx. So h cross by I and x are out of the differentiation part, then only del psi x by del x is left first of all, and then if psi x is constant, then differentiation of x is 1. So here only psi x. This is actually type of ddx of u and v, isn't it? U dx plus v du. So this is like that, and here the result is x h cross by I, then del psi x by del x plus then this h cross by I will also be multiplied with this one also. So here it gives the result h cross by I psi x. Okay, and finally we have to just here in the left hand side we had px cap x cap. This operation is done. This is the result of this operation. Now the reversed operation we have to do. The reversed operation is what? This one. First operate by px cap, then multiply with x. That means operate by x cap. So this is simply differentiation of psi x with this del x multiplied by h cross by I, and this result is then multiplied by x. So this is the final result of the reversed operation. Now what about their difference? The difference is nothing but this one minus this one. Okay, and this definitely cancels this term. This term definitely cancels this term, but this term is left. So their difference is actually h cross by I psi x. Okay, that means this operator is h cross by I. So the value of the commutator is h cross by I. Okay, so the correct option is this one. Option D is the no, h cross by I, this one, A. Option A is the correct answer. So that's all for today's lecture. Thank you and have a nice day.